Okay, so welcome back to our Q3 review. These are the last few pieces, the last few concepts that you need to know. So I just wanted to go through these last couple of concepts because they weren't included in the initial video. So turn to the next slide, please. And notice that in front of you are all the formulas on table T of your reference table. The calculations that you will need to be able to make for this particular third quarter test include mole calculations, percent error, percent composition, concentration problems such as parts per million, molarity, using the combined gas laws, heat, and, and converting temperatures. We've already gone through most of these on our previous PowerPoint. However, I wanted to take some time to explain to you when to use certain formulas. For example, if you turn the page or to the next slide, you'll see that you need to know the difference as to when you're going to make mole calculations versus when you're going to solve a concentration problem or for molarity. For example, if you look at the first question on this slide, it says how many moles are in 168 grams of potassium hydroxide. So you need to convert from grams to moles. In that case, you are going to use the mole calculation formula. Moles equals grams given divided by the GFM, or the gram formula mass. Now you are given 168 grams. So that's the grams given. So we don't know what, and we're looking for how many moles. So moles is the question mark here. So we say X equals, we're given 168 grams, 168 divided by, and now we have to find the GFM. The GFM of KOH is found in the following way. You figure out what elements you have. We have potassium, oxygen, and hydrogen. We figure out the number of atoms of each that we have. There's one atom of potassium, one atom of oxygen, and one atom of hydrogen, and we multiply that by their atomic masses. So for example, potassium has an atomic mass of 39. So we do 1 times 39, and oxygen is 16, so we do 1 times 16, and hydrogen is 1 times 1. We multiply it out, 39, 16, 1, and then we add them together, 15, 16, 4, 56. Okay, so we get X equals 168 divided by 56. When we divide 168 divided by 56, we get 3. So X equals 3 moles. So we solved for the number of moles. Now, if we want to find molarity in this second question, we need to use a different formula. We're finding the molarity of a solution that contains 4 moles of sodium hydroxide solution in 500 milliliters of solution. So now our given is moles. We have 4.0 moles, and we have 500 milliliters of solution. So we're given moles, and milliliters is a volume. Okay, so that's a different formula. That's our big M concentration molarity formula, which is molarity equals moles of solute over liters of solution. Now, a couple things are important here that you realize. First of all, molarity is capital M. That's the units for molarity. That's capital M. Whereas moles is MOLS. That's not just M. Lowercase m is meters, capital M is molarity, MOLS is moles. So it's giving you 4.0 moles. So in this case, we say, it says, what is the molarity? We don't know the molarity. The molarity is X. 4.0 moles is the moles of solute divided by, now it says liters of solution, and we're given milliliters. So we have to convert. We can use our kids chart. Kids hate doing units during certain months. And we realize we have 500 milliliters, and we got to get to liters. 1, 2, 3 places. We move the decimal to the left. So we get 0.5 liters. Now, we divide 4.0 divided by 0.5, and we get 8. Now your answer can be written with 2 different units. It can either be written moles per liter, or, so 8 moles per liter, or you can say 8 capital M, molar solution, because molarity is a measure of concentration. Okay? There's one more type of mole problem that you should be familiar with. This one is a mole-to-mole problem, and it's when you're given a balanced equation but not given grams. So you're just given moles of 2 different substances in a balanced equation, and you're asked to figure out how much moles are either consumed or produced of one of the substances in the equation. Let me give you an example. So how many moles of water, so we're looking at water, so we look in the balanced equation, we see water here, will be produced from the complete combustion of 3.0 moles of C2H6, that's ethane, according to the following equation. Well, we learned that these coefficients in front of the compounds or elements in a balanced equation represent a mole ratio. So we know that if 2 moles of ethane are consumed, that 6 moles of water are produced. But it's asking us what happens if we have 3.0 moles of methane consumed instead of 2.0 moles of methane consumed. So we're going to set up a proportion. The easiest way to do this is to take the 3.0 and put it over the particular compound that in the equation that you're referring to. So it says 3.0 moles of ethene, so we're going to put the 3.0 moles over the ethane. And it's asking us how many moles of water. So we're going to put X over water. So originally we knew that if we had 2 moles of ethane, we would get 6 moles of water, but we don't. We have 3 moles of ethane, so how many moles of water are we going to produce? So we can set up a proportion. 3 over the coefficient, which is 2, equals X over the coefficient, which is 6. We cross multiply, and we get 2x equals 18. We divide both sides by 2 to get x by itself, and we get x equals 9 moles. Excellent. Be very careful not to get confused between moles and molarity. Okay, the very last types of problems that we're going to go over have to do with nuclear chemistry and their nuclear transmutations. Remember, a transmutation can be identified because you have different elements in the reactants and the products. One element is changed into a different element. Okay? This first problem, right here, I'm going to put a 1 next to it. That is a natural transmutation because you have one substance, one element that decays naturally into another element, and then some type of particle or radiation is given off. So let's see if we can figure out what this particle is. Remember, by the law of conservation of mass, the mass of the reactants has to equal the mass of the products, and the same thing as far as charge, the charge of the reactants have to equal the charge of the products. So on the reactant side, we have a total mass of 131. On the product side, we also have a total mass of 100. We need to have a total mass of 131, and we do already have 131 as our mass. So the mass of our new particle is going to have to be 0. Now the charge. Iodine has an atomic number of 53. So altogether, we have a charge of 53 on this side. On the reactant side, on the products, we have 54. Xenon has 54 protons. How can we match the charges on both sides? Well, what we need to do is we need to subtract 1 from 54 to get 53. So this number down here would have to be a -1. If you go and you look on table O, you should be able to find the particle that has a mass of 0 and a charge of -1. And you would see that that's an electron or a beta particle. You could write it either as an electron like that, or you could write it as a beta particle. Excellent. Now let's look at this second type of equation. This one we said, the first one we said was natural transmutation or nuclear decay. The second one is different because you have a particle bombarding another particle, which is causing the nuclear reaction to take place. This is called artificial transmutation. And you should be able to recognize that this is a very special type of artificial transmutation. When you have either uranium or plutonium that's being bombarded by a neutron and splitting the uranium into 2 or more smaller particles, or 2 or more smaller elements, you should realize that this special type of artificial transmutation is called nuclear fission. Fission is like a fissure. It's dividing one big thing into 2 smaller things. That's different from nuclear fusion. Nuclear fusion would be having 2 small things rather, like hydrogen plus hydrogen to make one bigger thing, helium. Let's make this 2 and 2, so we get a helium particle. In both cases, a tremendous amount of energy is being released. So this nuclear fission equation is asking us to find x, and we do it the same way that we did it up above. So we look at the masses first. So we have a mass of 1 in the neutron and 235 in uranium. So 235 plus 1 gives us 236. On the other side of the equation, on the product side, we see that we have a mass of 141 for barium, and we have 1 for the neutron, but we have 3 neutrons. So altogether, we have a mass of 3 for the neutrons. So we have to add 141 plus 3, and we get 144. And we realize that we need to equal the product side. The masses have to equal the reactant side. So we have to subtract 144 from 236 to get 92, and that's going to be the mass of this new particle, 92. Okay, then we have to look at the charge. So we have a charge of 0 on the neutron and 92 protons or positive charge on uranium. So we have a charge altogether of 92 on the reactant side. On the product side, we have 56 protons in barium and a charge of 0 for the neutrons. 3 times 0 is 0. So we have 56 altogether, and we need to get 92 on the product side to match the reactant side. So 92 minus 56 is going to yield 36. So this particular element has to have 36 protons. And if we look up, we go and we find the element with 36 protons, because you will always look for the number of protons or the charge. Remember, the number of protons is how you identify an element. And so you look for 36 on the periodic table, and you realize that's krypton. So if you want to rewrite this element in isotopic notation, be 9236. Okay? Excellent. Last type of problem we're going to do today are half-life problems. Take a look. Okay? A half-life is the amount of time it takes for half of a radioactive sample to undergo radioactive decay. So let's solve these half-life problems together. A radioactive element has a half-life of 2 days. Which fraction represents the amount of the original sample of this element remaining after 6 days? Okay? So a radioactive element has a half-life of 2 days. So if we're going to so we want to know what our original sample is. A half-life we represent by an arrow, and we want to find how much, what fraction is remaining. A fraction represents the amount of an original sample remaining after 6 days. Okay? Now if we're starting with a fraction, we always start with a whole, which is 1. Then, okay, each half-life is represented by an arrow. And in this case, the half-life represents 2 days. So after the first half-life, half of the original sample is remaining. Okay? That's after 2 days. But how many half-lives do we need for 6 days? We take 6 and we divide it by the half-life 2, and we realize we need 3 half-lives, or 3 arrows. So we have 1 arrow, we need a second arrow, and a third arrow. 1, 2, 3 half-lives. So after the first half-life, we realized we only had half the sample remaining. After the second 2 days, we have half of that, half of the half. So we have a quarter of the sample remaining. But we're still not there because we have another half-life, 2 days. And after that half-life, we're going to have 1/8 of the sample remaining. So if you see, 2 days, 4 days, 6 days have gone by. After 6 days of the original sample, we have 1/8 of that sample remaining. Okay, let's look at a different problem and see if we can figure out how to solve this type of half-life problem. This is asking us for the total mass of radon-222 remaining in original 160 milligram sample after 19.1 days. Now, there's a couple things that we need to do here. So, first of all, we see what is the original mass of the sample. Remember, this box represented the original mass, or the original fraction, okay, the original amount. If it was a percent, it would be 100%. In this case, the original sample has 160 milligrams. Okay? Now, it doesn't tell us the half-life here, so you need to go to Table N. And you look up on Table N, radon-222. And you see that radon-222 has a half-life of 3.823 days. And it's asking you how much is going to remain after 19.1 days. So again, we have to figure out how many half-lives have gone by. So we take 19.1 days and we divide it by the half-life, 3.823 days, and we figure out the number of half-lives that have gone by. 19.1 divided by 3.823, and you get 5, approximately 5. Remember, we represent the half-lives with arrows, so we draw 5 arrows. 1, 2, 3, 4, 5. And then we, each time a half-life goes by, we divide the original sample in half. 160 divided by 2 is 80. 80 divided by 2 is 40. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. So the total mass remaining in an original 160 milligram sample after 19.1 days should be, if 5 half-lives have gone by, 1, 2, 3, 4, 5. Starting with 160, we should end up with 5 grams. Now, the last thing I want to tell you is you have to just be careful what the question is asking. It might ask you, it might say, how much did you start with? If you ended up with 5 milligrams, what was the original sample? And you would do the same thing. You would just work backwards, and you would double the original sample every time to get to an original amount. Okay, so I think we've gone through everything that you need to know for your quarter 3 exam. Good luck. Let me know if you need help. We'll be there after school on Thursday and before school on Friday morning, and available by email. Good luck.